Okay, we're talking about collections in general. All the material this week comes from Chapter 5 of the textbook, if you're reading along. We talked about how programs process data, and how important data is. And we learned about grid, a two-dimensional collection of data. And that's just one of many collections that we're going to learn in this class. And the next collection we're going to learn about is called a vector. Now, you might wonder, why are we not just storing data in arrays? I think I mentioned this briefly last week. C++ arrays suck. That's the short answer. They don't have a lot of features, and they are not very user-friendly, so that you're likely to have certain bugs when you use them. I mean, they do exist. C++ does have arrays. They just aren't built for new programmers, I think, and it's easy to mess up when you use them. Also, they just aren't very powerful. They don't have a lot of functionality. So we're just going to start with something a little easier and a little more muscular than an array. A particular thing that arrays do poorly in C++ is what's called bounds checking. If you try to walk off the edge of the array in C++, it does not give you an error. At least it doesn't always. In Java, maybe you encountered this. Maybe you're using an array in Java or an array list in Java, and you tried to put in a big index that was too big for the collection. And your program crashed with some red error messages or something, right? It's called an exception. In C++, you don't necessarily get an exception. Instead, the program just walks off the end of the array in the computer's memory, and whatever was after the array in the computer's memory, it stores your data over there. And so that could do anything. That could overwrite other important parts of your code or your program or who knows what. And in fact, a lot of classic bugs related to security and hacking involved tricking a program into overwriting parts of itself to cause mischief. It's called a buffer overrun. Anyway, C++ arrays make it really easy to mess up and do that. So we don't really like C++ arrays. So we're going to avoid them for a while. Okay, anyway, instead of an array, we're going to use collections. And I already kind of mentioned this. Collections are objects that store data. The data inside of a collection is called the elements. Every collection has a certain set of operations that it supports. Almost every collection supports at least adding and removing data. It's a fairly straightforward thing. You need to be able to put data in there. A lot of collections support some sort of searching function or looking for something in the collection. Some collections are faster for searching than others, etc. Some collections sort the data into a certain arrangement or order, and others don't. And there's all kind of different variations. Some collections allow duplicates, and others don't, and so on. Now, there's two levels on which you can learn about a collection. One is you can learn how to use it as a client, as a user of that library, you might say, to solve problems. And that's what we're going to do this week. We're going to learn how to use several collections. There's another level on which you can learn about collections, which is learning how they really work on the inside. I mean, think of anything complicated that you use, like a car or an iPhone or something like that. You can learn how to use an iPhone, but you don't understand all the circuitry inside of it. Well, there's a similar thing going on here. These collections are useful, and of course there's just code inside of them. We could open up the code and look at how they work internally. That's a little more complicated, so we're going to come back to that. The part of what we're going to do in this course is we are going to learn how all these things internally function, and that's part of the class. But we'll come back to it. We won't do it right away. Okay, what's a vector? Well, that's the first collection I want to talk about today. And the shortest answer I can give you is it's almost exactly the same as an array list in Java, if you are familiar with that, if you remember that from 106A. It's basically a collection of elements that all have indexes, integer indexes associated with them. And the first one is index 0, and the second one is index 1, and so forth. You can add elements to the list at any position. Initially, the list doesn't store any data, but you can add data to the list, and it grows accordingly. So some people say that an array list or a vector is like an array, but arrays have a rigid size. When you create an array, you say it has 10 elements, and the elements are all empty, and you can put things in the boxes. But a vector is sort of like a perfectly resizing array. It starts out as a size 0 array, and then if you want to put something in, now it's like a size 1 array. And if you want to put something else in, it becomes a size 2 array. So it's like an array that shrinks and grows as needed. That's not actually what exactly is happening, but that's how you think of it. Anyway, if you want to use arrays, there is a library that we provide called, or excuse me, if you want to use vectors, there's a library that we provide called vector.h that you can include in your project. Here's a couple of examples, like when you make a new vector, it's got nothing in it, and then if you add several strings, now it has grown larger to fit them, and so on, right? And the vector has some operations you could use on it, some methods you can call, and it keeps track of things. Like it keeps track of the data inside of it. It also keeps track of how big it is, how many slots it has, and all of these different things. It takes care of all that for you. When you construct a vector, you use the same sort of syntax that I showed you for a grid. You write vector and then the angle brackets, and you write the type of data that you're going to store in the vector. Vector is one-dimensional, though, not two-dimensional. So we already talked about that. It's called a type parameter. We say that vector is a parameterized class, or sometimes we call that a generic class. In C++, the mechanism for generic classes is called templates, but we don't need to worry about that yet, really. Anyway, you can construct a vector, and then you can say add, insert. I'll show you what all the methods are in a second. One thing I don't know if I really pointed out very clearly last week is that the syntax for creating an object is a little different than Java, right? In Java, if you were going to make an array list or something like that, this wouldn't be enough, right? You would have to write a little bit more. What's missing if this were Java? You'd have to say it equals a new vector or something like that. That's a Java thing. You don't do that in that same way here in C++. Just by saying vector string names, semicolon, that's like saying new vector. It makes the vector, creates it, constructs it, however you want to call it. So at the end of that semicolon on that first line, the vector lives, it exists, it's ready to use. So just a little bit different syntax. I mean, every year when I teach B, there's a few students who write equals new. It just doesn't compile that, and it's an error, and the student is confused because they're trying to write it the Java way. Anyway, watch out for that. OK, here are the methods that a vector has. It's got adding. It's got getting and setting. You can insert and remove. You can ask for the size. You can print the thing with a toString method. One thing that's kind of cool about vectors that also was available in a grid is that you can get and set the index values by using brackets, just like you would have with an array. In Java, with the array list, you have to call get or set methods to pull the data out. And here in C++, we can use the brackets, the square bracket operators. Another thing that's kind of interesting, when you add something to a vector, you can actually use plus equals. I'd say that at the top left of the slide. You can use plus equals to add something to a vector, and now the vector will be bigger. So I can show you just a quick example in the Qt Creator. I'm going to go over here, and let's find main here. So here's main. Sorry, I have some code in here from earlier. So here's main. Let's see, did I shrink this font? That looks a little smaller, doesn't it? Where are the settings in this dumb thing? Options. Oh, font. How about 20? There we go. Nice big font. OK, if you want to make a vector, you can just say vector int v. And now I'm storing integers in there. Initially, it doesn't have anything. So I can say v.add 42, v.add -17, v.add 29, and so on. And now you could print the contents of a vector, cout v endl. So if you print that, it's a little bit like saying toString in Java. I'll compile this and I'll run it. I'm getting some warnings, but that's because I have some functions up above that I'm not using that we're going to write today, so that's nothing to worry about. I run it, and it says 42, -17, 29. So the elements that I added are appearing here in the vector. I can insert and delete and change this at any index I want. So I can say v.insert. Actually, let me do this after I print the vector. I can insert at index 1 the value 999 or something. And I can print the vector again. And now the 999 gets inserted just before index 1. So it slides everybody over, and it puts the 999 before them. If I wanted to replace the -17 with the 999, what I could have said instead was I could have said that I want to set index 1 to be 999 instead of insert. Or the sort of shorter way to do that is you say v.1 equals 999. You see that? That's just, C++ will let you do that. Maybe I'll demo that by saying, OK, I inserted the 999 and I print it. Now I'll change it to 444 and I'll print it. And there. So you see before and after that, I can modify particular indexes in place. So it's fairly straightforward. And if you've used an array list, most of these methods are supposed to be, this library is authored by us here at Stanford. And we had heard of the Java array list when we wrote this library, so it's intentionally similar to that, to being familiar to you guys coming from Java. Any questions so far about what a vector is or how it works or what these methods are doing so far? Yeah?
How to remove only one element?
If you want to remove only one element, okay, sure. There is a remove method. So let's decide I don't want 444 there anymore after all. So I can say v.remove, and it asks for an index. And so I'll just say index 1. So I'll print it again and run it again. And now the 999 that I changed to a 444 is now just gone. And one thing you'll notice is that the other elements sort of moved over to the left. So there's not like a gap there or something. It just, that element number 1 is not there. The one that used to be 2 becomes 1. This is how an array list works also, right? Okay, good. Any other questions so far? Okay, well, one thing, I was just kind of saying this a second ago, but let me point it out more explicitly. By the way, you see that little blue logo thingy, right? That means I'm about to ask you a Socrative question in a minute. When you say insert at an index, C++ goes to that index and slides the elements over to make room to make an empty spot at index 2, and it inserts your new value, 42, at that spot. And when you remove from an index, oh, do I have an animation? Is that why it doesn't show? There. Okay, if you say remove index 1, it goes to that index and it says I have to get rid of this guy, so it slides everybody over. So now there's no gap there, right? So keeping that in mind, let me ask you a question. So let me jump to my Socrative. Don't read each other's email address. I wish there were a way for me to hide that. Oh well. Quick question, multiple choice. So here's my question. Here's a piece of code where I've created a vector, and I've added the values 10, 20, 30, up to 80 in the vector. And now after that code, I run this piece of code on the bottom. So what's the contents of the vector after that code is done running? Take a look and vote what you think is the right answer. And please feel free to talk to your neighbor if you want to. Let's give it a few more moments, and then I'll show you your votes. So make up your mind. Let's see what you guys thought. So the most common answer so far is C. And C is 20, 40, 60, 80. Yeah, I think that's right. Now, on the surface level, this code looks like it should remove everything, doesn't it? Remove everything from 0 to size. Doesn't that mean remove all of them? Can somebody give me intuition why it's 20, 40, 60, 80, like in English, kind of why is it? Yeah.
So what happens is that when you, for the first one, cycle through that loop, you're doing what it looks like you should be doing. I is 0, the vector size is 8. It removes the 0th element from its vector size 8, which is 10. Then it goes back to the conditional at the beginning of the 4, and now vector size is 7, and index is 1. And also everything has been shifted over by 1, so the 20 is now in position 0.
Okay, wait, what you said there was really important. So you said, let me just, wait, can I just draw this? Wait, how do I make these go away? Okay, I got a magic pen here that I can draw. So if int I starts at 0, so int I is right here, right? That's what you said. And so I delete the element 0 right here. But that turns all these indexes down, 0, 1, 2, 3, 4, 5, 6, like that, right? And you said, so I mean, if int I is at 0, int I is actually at this point right now. And you said then the loop wraps around, and I do I++, and that means I becomes 1. So now I is there. And so the next time I do a delete, it's the 30. Do you see that? So the 20 got skipped. So yeah, the shifting kind of makes this not delete every element the way that you might otherwise think. That's exactly right. So that's my trick there. Of course, most of these questions are designed to aggravate you and trick you and frustrate you and all that stuff. So yeah, I mean, it deletes every other element, even though it looks like it would delete them all. Of course, if you wanted to delete them all, there is a method called clear that just deletes everything. So you don't need a loop for that. I'm just pointing out this is what this code does, right? Okay, well, anyway, that's an example. There's another one on the next slide. Maybe what I'll do is instead of Socratoving this one, I'll just ask you to look at this for a second and just tell me, maybe somebody who decides that they think they know the answer, maybe raise your hand and tell me what you think it is and why. What do you think it is, sir?
I think it's going to be B.
You think it's going to be B? It's going to have a bunch of 42s at the front. Okay. So I think that's right. A lot of people either put that or the one that kind of alternates the 42s, right? Because it seems like if it's moving forward and adding 42s, maybe it would insert one after the element at index 0 and one of them after the element at index 1 and so forth. So why do you think they all clump up at the front?
Because it's going to, each iteration is going to shift the vector to the right. So then the index goes up 1. So they're just going to be one after another. It's not skipping anything.
Right. Like I add one of these here, and then everybody else shifts over. And then I add another one of these here, and everybody else shifts over. So as int I is moving, everybody else is also moving. So I'm still continuing to add everyone just in front of the elements that came before them. So anyway, I wanted to show you both of these examples just because a lot of people who write code that uses vectors end up falling into one of these traps where the vector is changing as their loop is going, and it makes the logic not match what they would have thought. Yes, sir?
When you initialize the vector, you added values into indexes 1 through 5, but the first index of a vector is 0, right?
Oh, you're asking about what I added to the vector here. Well, I'm saying for each int 1 through 5, I do plus equals 2 times I, but I didn't say what index. So plus equals means add to the end of the vector. So it's adding the first one at 0 and the second one at 1. So it's like adding, those at the first 5 indexes. Okay. So anyway, I just wanted to build some intuitions about vectors and how they work. So let's try writing a little bit of code that uses a vector now. Okay. So let's write a method called countinRange, where you pass in a vector and a minimum and a maximum, and you return how many elements in the vector fall within that range. Okay, so if I have this vector right here, and I want the counting range from 10 to 30, it would notice that these 4 elements are within that range, and it would return 4. Okay, so we're just practicing a little bit here. So if we want to do that, let me show you something cool you can do with a vector in main here. Maybe what I'll do, if you don't mind, I'm going to comment out most of this code that we wrote earlier. You can say v plus equals and then put lots of values separated by commas, and it will add all of them. That's kind of sexy, isn't it? And so now Let's just recreate this example call from the slide. We'd probably want to test it with other calls later, but let's just start with this one. If I want to do count in the range v from 10 to 30, I'd like that to do 4. So I'll say like int count equals that, and then I'll say cout, the count is count. And then, of course, if you count anything, you say right? You people probably don't watch Sesame Street anyway. Never mind, but whatever. So now I have to write this count in range. And I've already declared it up above to help us get started on it. So one thing I want to point out about this heading for this function is that we're accepting a vector and a minimum and a maximum as parameters, right? But I want you to remember this character, right? Why am I passing the vector with an ampersand? I mean, that means by reference, right? So what's the benefit of doing that?
It doesn't take up as much memory because the program doesn't have to create a new vector.
Yeah, if I delete that and I just pass it, it means I'm passing it by value. I'm going to make a full copy of all the elements of the vector as I pass it along. There's just no need for that. I'm not going to change it or mess it up. I'll just share the vector from main to here. That's faster and doesn't use as much memory, like you said. So I'll pass it as a reference to a vector. So how do I actually compute this? There's several ways you could do it. Like, what's the straightforward way using what we've already learned in the class so far? Yes, sir. What do you think?
Loop over the elements and add to some function.
Loop over them? OK, so for int I is 0, and I is less than the vector size. OK, sure. And then what do I do to each one of them?
If it's within your limits, you add 1 to some function.
OK, if it's at least as big as the min, and it's also no bigger than the max, then I need to count how many of those I've seen. So if you're accumulating things and counting up things, usually you make like a variable outside here, right? Count equals 0, and then you say count plus plus, and then you return count. You guys remember this kind of stuff, right? So you have to keep some kind of accumulator or variable for this stuff. OK, sure. Let's try it out. Down here in the main, I think I commented everything except this thing that we're running to test. So let's compile it and run it. And the count is 4. So I think that was the right answer. I mean, from this call on the slide here, it was supposed to return 4. Let me mention a couple of other things. So if I go back to the count in range, like one cool thing about Qt Creator, like sometimes you're sitting here and you're like, yeah, I'm calling this function, but now I want to like see the code for that function. Well, you can right-click it and say follow the symbol. And I think the default hotkey for that is F2 if you just want to become a keyboard jockey. But if I just push that, then it jumps me up to there. So you can learn some of these keys to bounce around here and jump places. But anyway, I want to mention one other thing about, I looped over these elements from 0 to size. I want to show you there's actually another syntax for looping over a vector. I mean, this is totally fine right here. But let me show you another example. Where is it? Here. There's something called a for each loop. For each loop, there's one of these in Java as well, where it just allows you to loop over a collection without using the int indexes and stuff. You just say kind of for each integer in the vector, for each string in the vector, I want to call it s and print it, or call it something and deal with it. So the thing that confuses some students is like if you look up here, the loop is over a range of integers, and you use the integers to access the strings that are inside the vector. So like there's a separation here between indexes and pieces of data. The pieces of data are associated with the indexes, but we're only really using the indexes up there to get to the pieces of data that we want to print. So down here, we just forget about the indexes. Just for each of the strings that are in that vector, call them s and then print each one of them. That's what this second form means. So like back in the code that we were working on, instead of saying for each int I from 0 to size, and vi less than whatever, I could just say for each int number that's found in vector v, then I could say like if num is at least min and num is no more than max, then I'll increment my counter here. That will do the same thing. Yeah.
But when you use this for each loop, if you do the same thing as the question, which is like remove or insert in the vector, will the same thing happen?
Yeah, her question is like, what if I'm doing something to modify the thing, like removing from the vector, or if I wasn't just printing them or doing something simple with them, I probably would use the index version of the loop. The for each loop that I just wrote now is really only for like looking at them, reading them, not changing them. If you're going to be filtering them out or deleting them or reordering them, you probably don't want to use the for each loop for that. But this is just a slightly cleaner syntax for what turns out to be a pretty common task, which is just loop over the elements and do something with each one of them. That's what this syntax does pretty well. So anyway, there's nothing wrong with the first syntax, but I think if you just kind of compare the two of them, in this particular kind of a usage, the for each loop is a little bit cleaner. And again, I want you to understand that this int num is not an index. It's the actual elements of data that are inside the vector. That's what I'm looping over with this new loop. Well, maybe to come back to what she asked about, there is this problem called remove all on the slide. So it accepts a vector of strings and an element value, and it deletes all occurrences of that string from the vector. So if I say remove all the b's from this vector, then I will get ACA. So maybe I could set that up and call that real quick. So let me grab this, and let's go to my main. And let's make a vector of strings called v2. And let's say v2 plus equals, well, they're not in quotes, so, OK. Ready for some ninjutsu? OK. Let's do comma becomes quote, comma, quote. Bam. OK. There we go. And then paste, semicolon. So now we want to remove all the b's from there. So I want to be able to say remove all from v2, all of the b's. And then hopefully when I'm done, if I do cout, after remove colon, then I'll get v2. And hopefully that'll have the b's gone. So if I jump up here, I'm going to hit that F2 hotkey and jump up. I've already written a heading for this. From this vector, remove that string s. And now we need to write it. So your question was a good one. You were asking, could I use a for each loop here? And the answer to that would be no. Like, you don't want to use a for each loop here because if you're modifying the contents, you really want to use the indexes instead. So I mean, I could steal from ourselves. We were up here. We had a loop like this that looped over all the elements of V. Somebody help me. What goes next? Like, what do we do to each one of those elements? Do you understand what I'm doing here? Like, this string S is the string B in my call from main. So I want to find all the B's and get rid of them, basically. So like, what do you want me to do inside here? Yes, sir? Yeah.
So for each index, you would check to see if the string at that index is equal to the string s.
OK, check if it's equal to s. So if the element I is equal to s, careful, don't put quotes, right? Then you're going to literally look for the letter s. That's not what I want. If it's equal to s, then I want to get rid of it, right? So v remove, you have to pass an index to remove from, and we're currently looking at index I, right? So OK, sure. Let's try it. Oh, some of you guys don't like the code. What do you think, sir? What's wrong with the code?
Well, I think the problem is that, like we saw before, it'll like jump some because if you remove like the first element, then I will go to 1, so it'll go to what would have been the third element instead of the second element.
Wait, you're saying that this solution will jump over some of the ones, it won't remove all the ones that it's supposed to remove?
Exactly.
So you're calling me stupid then, are you? You saying you can code better than me? Well, maybe you can. Let's run it and see if you're right. A, C, B, A. Hey, I thought I told all those B's to get out of there. But just like after too much partying on finals week, a B slipped in. So, and a C too, right? Uh-oh, that's even worse. Well, we didn't say to remove the C's. So, yeah. So if you're following what he said, which is totally right, like if you remove the elements, like think of int I as being like a little cursor. Like, if you delete B from here, the elements get deleted, and then int I shifts up. So it's like if you see a B right here, you go, oh, it's a B, I should delete it. So you say v.remove I, and then you separately say I++, which does all of that at once before it checks anything again. So you don't actually ever check the second B to remove it, so it doesn't get removed, just like what you said. And so we have that one B that's left in the array afterward. That's the bug. So OK, how do we fix the bug? bug. What do you say, Miss? Yeah.
Like I have two solutions. One is to use like I minus minus immediately after.
Okay, I minus minus.
The other
Okay.
one is just make a copy of the vector and then you just remove.
Okay, those are interesting ideas. So one solution she says is just do I minus minus. So like if you delete here, then your variable, your sliding will go like that. And then you're saying do I minus minus, which then when the loop wraps around, you'll do an I plus plus, which will kind of back and forth you back to the same place, but that will make you check the next B the next time. So that totally does work and fix the bug. Her other suggestion was maybe I make some kind of V2 here and make another vector and copy things across and stuff like that. And you can definitely solve this problem that way, but I kind of like trying to solve it just with the one that we have. And so I actually like your first suggestion better. Let me see if your first suggestion works. I mean, those are both ways you could potentially solve this problem, for sure. So now the B's are gone, so that totally worked. There's another way that you could get rid of the B's and not have the bug without having a secondary vector. Do you guys know any other way of getting around it? Matt, what do you think?
Do the vector backwards?
Loop backwards, yeah. So if you start at v dot size minus 1, which is the last index, and you go as long as I is at least 0, and you do I minus minus each time, then without the, I didn't have to monkey around with I here. I just remove things, and all the B's got deleted. And if you just think about why for a second, it's because as you go backwards, you delete this B, and then, okay, fine, no problem. Now you I minus minus, that's not a B. I minus minus, oh, it's a B, I'll delete it. Oh, I guess my example was supposed to have 2 B's in it, so let's assume that I'm right there. Oh, it's a B, I better delete it. Then I minus minus, so I'm just still right there ready to look at the second B. Yeah, so sometimes going backwards is the way to do it. Kind of like on that TV show Lost. We have to go back. I don't know if you guys ever saw that show. But it's a good show. Check it out. So yeah, a couple different ways you can get around this issue. Iterating backwards or doing I minus minus. Those both work great. Any other questions about the vector code that we've been writing so far? Those two examples make sense? Okay, I want to talk just briefly about a second structure and about some general concepts about differentiating data structures called abstract data types. If you could crack open a vector and look inside, what you would see is that there's an array inside. I told you a minute ago that maybe we didn't want to use arrays directly in this class. So maybe it's confusing that I tell you that there's an array inside of a vector. But the idea is it's like a layer of protection. The vector is like a smooth coating around that yucky, it's like a milk dud, it's got yummy chocolate on the outside and poison on the inside or whatever. Protects you from that stuff. So inside of a vector is an array. And one thing that's interesting about it, we'll talk more about this later, but sometimes the array is actually bigger than the vector seems to be. Like even though you've only added 3 things to the vector, internally its array might have 10 slots or 100 slots, but just you don't use some of those other ones. But that's just kind of a detail for later. But okay, if you think about some of the operations that a vector performs for a second, just think about what might the code of that operation look like inside of the vector. If you say insert at index 3, I have to put the new value right there at index 3, right? So what do you think the code is doing to accomplish this? How do I fit that in there at slot 3? What do I have to do first? In the glasses, yeah.
Yes, it's just shift the memory address of the following arrays by 1 and just put that into the new memory.
Right, I have to go to all the elements after the one I'm inserting, and I have to move them over. You said like increase their memory address a little bit, right? Yeah, so I mean if you just think of it as ints, like a bunch of ints, I have to like move all the ints over by 1. It would be like if, how there's no real estate in Palo Alto, right? So you get this bright idea like, well, I'll just live across the street from Stanford. All I got to do is lift up all the other houses and move them over by 1 lot, and the last guy gets moved into East Palo Alto. That sucks. And then I get this first slot, right? I think you would understand the idea that the more people you have to move over, the longer it's going to take, right? I mean, in housing for sure, but here as well. Like, what if, I inserted index 3, What if there's a million elements after that? I got to move all million of them over. You'll have to take my word for it that it takes longer to move more things. So that means that inserting stuff into the vector can take a while just to insert one value because of all that shifting, okay? Well, so one thing maybe I'll ask you is, what is a place that you can insert in the vector that's not very slow? At the very end, there's no one that needs to be shifted. The end of the vector is the East Palo Alto of the vector. Lots of space over here. Come on in. Anyway, I'll just keep moving. So linked list is another collection that exists in our library. Now, what's a linked list? Well, it's basically the same as a vector in terms of it provides all of the same operations. You can create one. It stores things with indexes. You can access it with the brackets. You could add, remove, all the methods, like literally all the code we wrote today, if I just did replace and I replaced vector with linked list, the code would then compile and run fine. It behaves the same. So that might be surprising to you. Like, why would they include 2 copies of the same, basically the same library in here? What's going on? Well, it has to do with the internal structure of the collection. Inside of that linked list thing, instead of creating a big array to store all the data, it has a bunch of little boxes called nodes that store data. And the boxes are connected by little links to connect them together. Which, I'm waving my hands a little bit. I'm not going to talk about exactly how it does this. But the nodes of data are little individual boxes. OK, well, what does that mean? Well, when you're using it, when you, the client programmer who's using this thing, when you call those methods, you don't have to do little boxes and arrows. That's not something you have to worry about. That's going on internally. But the side effect of that, it has all the same. I'm not going to spend time on this slide. It has the same methods as a vector. The side effect of this is when you want to insert something into a linked list, the mechanics of that operation are now different. Instead of going to a certain slot and then sliding everybody over, what the list really does is, let me try to draw a picture again here. If you want to insert something right here, like in between the 9 and the 7, you want to insert a new box. What you do is you take your little scissors and you snip this connection here. You make a new box up here. And you make this guy go up here. And you make this guy go down to there. And you just sort of insert one into the chain. And then the whole thing just sort of works. And so you don't have to shift anybody. That's the way that the linked list works internally. So that's kind of cool. It means that it's faster for certain operations. So maybe you're thinking, well, who needs a vector, right? If I've got a linked list, maybe that's better. Maybe that's faster. But there are some things that a linked list is not very good at. For example, when you just use the brackets to jump to a certain index in a vector, he was talking about, when I asked about shifting elements, he said, well, it just moves the memory address by 1 or something like that. And that's kind of the right mental model for an array. When you want to access different indexes of an array, you can immediately jump to any place in the array very quickly in the computer, because the array is all one giant brick of memory that's all right next to each other. And so you know exactly how many bytes of memory you have to move to get to any index. So it's really fast to jump right from index 0 to index 1 billion and back again. With a linked list, you have to kind of walk along these little links to get from one index to another. And so if you're kind of jumping around a lot looking for things, it's slower for operations like that. And so one interesting thing about our library at Stanford, and this is common of many other collection libraries, is that they'll provide you more than one collection that does exactly the same thing. But the version on the right is faster for these 5 operations, and the version on the left is faster for those 4 operations. And you sort of pick which one is the best, depending on what your program is doing. So anyway, I've got a Socrative buzzer thing on the top of the screen here. So let me pop this up. And so what I think I'm going to do here is a quick question. So now if you guys can change your vote, right? I don't see the UI that you see. If you push one of them and then you change your mind, can you just push a different one? Does it?
As long as you do it before you click submit answer.
Oh, as long as you do it before you submit it? Oh, OK. Well, then I'll do it. OK, I'll do it different. So, well, go ahead and vote. You don't even know what you're voting for. I love it. I love the confidence. By the way, there's only 2 answer choices, and I love the people picking Deanie. OK, so here's my question. Which one of these collections do you think is faster for these given operations. So A for vector, B for linked list, C for about the same. We're going to go fast here, so just give me your first 5 or 10 seconds thought answer. Removing from the front of the collection, which one's faster for that? Vote A, B, C. Or if you want to raise a silent protest, you can vote D or E. Remove from the front. Who's faster? OK, let's see what you think. Votes are coming in about the same. So B is getting more votes. So removing from the front of a vector, you have to shift everybody to the left to fill that. And removing from the front means all of everybody needs to shift over. So that's slow for a vector. For a linked list, that's pretty fast. So the answer for that one is probably B. OK, so wait, now I have to say false, quick, multiple. So I just restarted again. Does it pop up a new one now for you? OK. How about removing from the back, from the very end of the structure? Which one do you think is faster for that? It hasn't popped for you? OK, well, it's OK. If you're voting on most of them, it'll still count you. Hopefully, the next one I pop will appear for you. Sorry. Removing from the back. Let's see what you guys say. So about the same has a lot, and vector has a lot. Well, those are both good answers. Removing from the back of a vector is very fast. You just jump there, you delete it. There's nobody to shift. So I guess removing from the back of the linked list depends on your interpretation of what I said previously. So it depends, am I allowed to start from anywhere? Do I have to start from the front and walk all the way to the back? Can I start from the back? Depends on the answer to some of those questions. So actually, since I've been ambiguous about that, I think either of these answers would be great answers. It turns out that most Most implementations of linked lists lets you start at either the front or the back and kind of walk toward the middle. That's often how you do it. So if that were the case, it would be C. But if it's more like this picture where you start at the front and walk to the right, then it would take a long time to get to the right, in which case the answer would be A. So I'll take kind of both of those as good choices. OK, let's do one more. So what about filtering out all occurrences of a particular value? The last one here. It's kind of like our remove all method that we wrote today. Which one do you think is faster for that? It depends how you write the code, doesn't it, right? So we can talk about that in a second. Maybe using the code that we wrote. Which one's better? OK, let me see what you guys think. Filtering out. Wow, that's great. It's all over the place. You don't freaking know, do you? I'm just kidding. You don't even know, man. Look at this. This is guessing right here. No. I think actually this one is very open to interpretation. So I think there's pretty good answers, pretty good validation for all these three choices. So filtering out the occurrences of a value. Well, it does depend how you write the code. So if you write remove all this way that we just changed it to, where you go backwards, it's faster than if you do it the old way with the I minusing, because the old way kind of repeatedly does some stuff. And also, if you start removing from the front, the shifting you do is going to be a little more shifting. Like if you just think about it in your head a little bit, you have to do a little more shifting than if you do the light shifts here. And by the time you get to the front, there's fewer people behind you to be shifted later. But anyway, with the linked list, you just start at the front and loop across. And it turns out if you want to delete somebody, like you want to delete this 30 right here, you just make the 20 guy's arrow point to the 40 instead, and it's very quick. So it turns out that the linked list is slightly better, but I think it's totally justifiable to say that they're both pretty good at that operation. So there's some operations that are better for one and some that are better for the other. And the kind of closing thought that I'll leave you with is this concept that you could implement the same thing two ways, and that neither one is just totally better than the other. Each one's better at certain things. That's called an abstract data type. Both vectors and lists implement the same abstract set of operations, but they do it in a different way. So we would say those are the same abstract data type as each other.